Hello, my friends. Good afternoon, good evening, good morning, whatever time it is where you are. Welcome. This is Dr. Mohamed Nezami coming to you from Garage, Jordan. I would like to thank you again to join me. Um, please, okay, this is my YouTube channel where these slides are going to be. And I would like to thank you. I would appreciate if you could please uh, subscribe to the channel, visit the channel, subscribe, and share the video. I would appreciate that. Thank you. Okay, so today I'm gonna basically continue my series. This is the fifth part in my KU band antenna LNB feed structure design. Okay. And so previously I have finished four parts, and you can see them there right here. This is part four, um, part three, okay, part two, and also part one, okay? So today, basically what I'm going to cover, let me just go ahead and give you a preview. Today I'm going to basically cover both rectangular, square and circular septum-based circular waveguide LNB feed structure. Okay, these are LNBs that are, let me jump ahead and show you. These are LNBs that are like this, okay, where we have a circular waveguide, which is this one here. This circular waveguide, this is the horn antenna, comes in, a circular waveguide passes a signal to the board, this board here, and this board has a septum, and we will talk about that in a minute, which separates the right and left polarization of the circular polarized signal. So, please, if you I would appreciate if you subscribe to the channel and share these videos. The last video number 4 was regarding the rectangular waveguides, okay? And we did cover that, and please go ahead and see that, and see the other portions as well, because if you're just happen to be watching this, please go back and watch the other ones so that you have a cumulative knowledge of what we're starting with. Okay, so basically today I've got the basically a square rectangular waveguide, septum based um, LNB feed structure basically. So we've got a square waveguide like you see here, and the septum inside of it, and then we have probes. The signal comes in and goes through the septum and gets septum polarizer depolarizes the circular wave and give you one right here and one right here. This here becomes a rectangular waveguides where you can pick up the vertical and horizontal. And of course, this board in here, this is a small piece of board, but that's really mimicking as if you have a board like this one here. Okay, so I'm just modeling just this piece in here, uh, so that this can be designed, modeled, optimized, and sent to the cadence schematics and BCB or Altium, whatever, so that you could integrate with the rest of the LNB. Okay, so let's get back here. So we're gonna have, like I said, we're gonna have the square wave one, and then we're gonna have the circular one with the probes, the circular one, same thing. Okay, and of course the aperture of the waveguide, I just removed the copper from it so that it actually it's right in the middle of the circle waveguide. And this part here is the extension, the quarter wavelength extension shorted back end, which you can see, which we will talk about in a minute. And of course, I talked about the design of these and design of the probe in here in the past sessions. So the next part will be to take one of these, and also here's another variant of this where the probes have a little cap to it so that you can actually tune it more. Okay, here's one where I go ahead and actually hollow the waveguide board. So the aperture of the waveguide is empty, but I keep a little piece of a substrate that has the probe on it. Okay, and this is another variant of this. So we'll talk about this, and so we have. Let's go ahead and cover some background, and we'll come back to the simulations. Okay, so like I said, my name is Dr. Mohamed Nezami. I come to you from Jerash, Jordan. That's the ancient city back there. As you can see, the colonnaded streets and Roman city. I'm a freelance, semi-retired RF and microwave circuit designer. I take contracts, small contracts, building, designing, and designing remotely, mostly for clients in the US, in Europe, India, Middle East, and some Asian countries, of any RF designs from DC to 35 gigahertz, basically. I I have a training also, and the training is basically really in here is actually nothing but the actual these videos. We go through these videos with you, the trainee, sitting and doing the hands-on building of these and other various stuff that I did on ADS and Cadence. So the next session is coming in April 22 to April 29. The cost is $2,000 per person. I handle the hotel and accommodation, transportation, and you handle, all you need to do is just make it safely here. Okay, so let's continue about the LNB feed structures. Now, last time we talked about this and we introduced the concept of LNB feed systems. And we can see that it varies from like large gateways or deep space probes or radio astronomy dishes to your KA or KU satellite TV broadcast stuff, direct broadcast TV. So basically, the pieces that we have in all of these systems, the signal is assumed to be circularly polarized. So we have a horn, circular horn that picks the circular polarized signal, and then it actually has an OMT, and you can refer back to my lectures in the video on my channel. You can see the design of OTMs and polarizers, and it splits the signal. So we can actually we have an LNB, which is the receive portion in here. So this portion in here is called the feed system, is how to feed between the LNA, LNB, and the waveguide feed to the antenna, and then also from the buck to the antenna. We get variations of this. We can have it like this, we can have it like this, or we can have it like this, which is a low-cost consumer type. Okay, in all of these systems, okay, the horn in the parabola, okay, is usually the signal is fed from the horn to either a square wave waveguide or a circle waveguide. Okay, if we have a circle waveguide, usually the TE mode that is dominant is TE11, and as you can see in here. Okay, and if the square waveguide, we've got two modes. We've got the TE10, which is what you see usually in rectangular waveguides, and then we've got another one, which is TE01, and you can see that this is vertical and this is horizontal, and the same thing applies here to the. So today, let's talk about, and I introduced this last time, we have 5 types of LNB feed types, okay? And I did show you this picture in here. The first type was the type that we spoke about in part 4, which is basically rectangular waveguide. Here's a probe, a rectangular aperture in here. and here's another probe that goes down into the waveguide. And then we've got this one here where it uses septum and circular waveguide, okay? And that's what we're going to talk about in part 5 right now, this session that we're in. And then we've got 3 more types that we will handle in the next coming videos. Okay, so this is a typical circular polarized circular waveguide septum-based LNB feed. That's this portion here, okay? So we've got the signal comes in, it comes in here, the parabola is here, it reflects all the signals, focuses all the signal, collects them and focuses them at the focal point, which is where this horn antenna is at. And then the horn antenna is connected to a circular waveguide. And then the circular waveguide takes the signal onto the board, which is here, and then gives you an IF signal in here, which is in the L band. Okay, 950 to 2150, 950 to 1500, something like that. So what you see in here typically is basically, as you can see here, is we've got 2 probes, okay, that are picking up 2 signals that are coming from a circular waveguide that got split into 2 halves. So this is circular tube in here, this piece in here, and this piece in here. And this really is an approximation of a square waveguide. Okay, so I mean a rectangular waveguide, sorry. So you get one mode here, and what we refer to them, usually depending on whether it's right-hand circular polarized or left-hand circular polarized. We get the signal, we go into a transistor in here, and a gas FET transistor, LNA, and then we go into another stage, and then we go further into the down converter. And the same thing is done exactly for this one. Of course, we have, after 3 stages of amplification, usually there is an image rejection filter, okay? And you can refer back to my video sessions on LNB designs, okay, where we design LNBs on System VU and ADS. Okay, so basically, now the loss in here in this feed network is very critical because we're trying to design this with a noise figure of at most 1 dB, okay, for the KU band. So as you can see, if this LNA device in here, if this chain, a 3-chain LNA KU band, you'd be lucky to design this for more than 0.7 dB. So they give you only 0.3 dB for this and the front end waveguide here. So it's pretty critical part. Now for square, these are the LNBs that you see that usually you see on your TV dishes. So here's one where the cover was exposed. Looks like this, but you can see the lid in here lifted up, and this is the board underneath it. And basically what we have is we really pick up the signals, 2 signals in here. This is, by the way, this is different type in here, but let's just go ahead and talk about it because we'll cover this next time. This is this type here, okay, which is type 5, okay. And what usually is that we get these modes in and we pick them with a probe, a pin probe, which is, you can see it right here, the solder bulb in here. Okay, here's one. And there should be another one, which is this one here, okay? And you can see that they're orthogonal. One goes down directly in the middle of the square waveguide to picks up the signal, and the other one goes along the side and it has a bend, which is this. There's a vacuum in here. This has this pin in here, goes down. It has an air chamber, and then goes 90-degree bend, and it actually goes into the waveguide and picks up the horizontal. Another variant of this is this here, okay? Now, for circular waveguide, as you can see here, it's exactly the same thing if it's pin done. So we got 1 pin in here, 1 pin in here, and you can see there is the LNA device and another LNA device, LNA. So this is for one polarization, and this is for the other polarization. Of course, we got 2 separate image rejection filters, and then we go into mimic down converter chip. So this is another type. This one in here is the same as this type, except it's circular waveguide, not rectangular. So in that one, we can get either a square waveguide or a circular waveguide. If you get a square waveguide like this, you only have to have a little piece that converts a transition from circular horn to the square waveguide. And that's this little flared metal in here. That's what this is, okay? And that's what this piece here. All right, so let's go ahead. So what we want to talk about today is the dual polarization circular, not square. I apologize for this, waveguide and septum LNB feed using printed probes. Okay, so we're going to use a septum and we're going to use printed probes, microscope probes to pick up the signal. And to do that, I had started a series of designs on ANSYS HFSS, starting out from a circular waveguide and a square waveguide, built a septum, both of them, tested it as a waveguide septum. It worked well, and then tested it another time with this one in here using a coaxial to waveguide transition, which worked well also. And then I did this, this is in preparation for this type of LNBs. Okay, so now what we're going to do is we're going to take this guy here, okay, or this guy in here and this guy in here, and add a small PCB board to mimic this portion of the board that is here, where it interfaces to the, that has the probes, and it has a septum and a waveguide, circular waveguide. And let's design and model this piece here. All right. So before we do that, let me go ahead and just make a slideshow of some of LNB boards that I happen to have in my junk box and some that were posted on the net. And these have been floating around. People have done this where they did tear down of LNBs or studied them or modified them. A lot of people, they get these LNBs and they modify them. They actually recycle the LNA or the local oscillator or the synthesizer if it's not DRO like this one. But let's just focus back to the portion, just show you a variation of the circular waveguide probe-based printed probe LNB feed architectures. Okay, so here's one board in here, and you can see here is the circular waveguide aperture, and here is a single polarization. We're picking up a single signal in here. Okay, so in this one in here, I don't see them picking up another signal anywhere. So this is just an interesting one. So you get the signal and you go into a gas fit amplifier in here, and then it goes through another stage of application, another stage, so 3 stages. And then here is a edge-coupled filter, which is an image rejection filter, feeding on to this one in here, where this one is really is a, this is a mixer, a dual Schottky mixer. And this is a DRO oscillator that basically beats with the incoming signal, produces an IF. And the IF is probably off the board somewhere right here, goes off somewhere else. Here's another one. And this one in here is what we're trying to model today. And basically what this is, so we've got this is a septum inside a circular waveguide. And please refer back to my other videos on septum designs, and you can see those. Let me just show you for a moment. We can see those right here. There's one, the septum design. I covered that previously. So let's see. You can go in and do your search. I have about 100 videos, and you'll find it. It's in there somewhere. Okay, here it is. Okay, so this session here, design of 3D modeling of KU band orthomode transducers. Okay, this one in here and this one in here, and here's one in here. These three videos, I talked about septums and septum design in there. Okay. So that's what it is. It's basically really you take a circular polarized signal and you end up splitting it to the left and right or right and left, whichever way is the rotation of the circular waveguide. So what we have the way we have this is that here's the horn behind. You can see it here. The horn comes in, it feeds the circular waveguide, which is this. This is the septum. Okay, this is a staircase septum, which splits the signal in two halves, one here, one here. And here's a little probe, printed probe, that has an extension that was laid out, printed on an extended little rectangle from the BC board that is doing the LNB, the whole LNB. And of course, this one in here, you need a back short. So what we do, we pick the signals in here, but we have an extension of a quarter wavelength cover on this, which is this lid in here. You see this lid? This lid comes in and covers this, and this will implement a short-circuited quarter wavelength waveguide suction on it's really circular, but this metal in here split it in half, so it's a semicircle, which implements a TE10 mode for circular waveguides. So let's just go ahead and build this and build this section in here, and that's what you're going to see today in here. That's what we're doing. That's what this piece is. This piece in here, as you can see, let me show you this one in here. This one in here is basically the extension, the quarter wavelength extension on top of the board. Okay, and so all right, so just I know that I'm not going to spend a lot of time on septum designs, but just to show you the principle, just as a reminder, if you didn't watch my previous videos, basically when you have a counterclockwise or clockwise rotated circular polarized signal, it's really as if it's a complex signal with real and imaginary, and that's what you get. So the septum comes in, and it's this stared metal piece in here. So in this case, it's illustrated for a square wave, because square wave, which has two modes, TE10 and O1, okay, in here, and it's the same as a circular waveguide, same exact thing. It doesn't change. The principle doesn't change. This can go in, and you can trace the interaction of the septum with both the vertical and horizontal. And what happens is you end up, depending on whether the mode E pattern is perpendicular in this case or in parallel to the metal pieces, you end up with the signal going in one half of the waveguide in here on the other side. So you end up being either here or here, depending on whether you're left or right. And that's how we decompose circular polarized signal into two portions, vertical and horizontal. Because in a lot of satellite systems, to maximize capacity, the same frequency has two, it's multiplexed, vertical and horizontal, with two independent data streams to double the data rate. So that's why we're doing this, really. That's the whole purpose of this, is to isolate them, okay? Otherwise, what you would need to do is, that one is phase shifted from the other one, so you can just basically get a 90-degree hybrid and combine them, and then you get double the power. That's if the signal happens to be in real and imaginary is the same. Like a radar, for instance, that's exactly the same. It's the same signal. Unless it's one of those exotic radar modulated binary type. So same thing is done with the circular waveguide, okay? So you've got 0 and 90-degree signals coming in, fed into the circular waveguide, and you end up with going into either this one or the vice versa. So it works out whether it's transmitting or receiving, it's the same thing. All right, so, and I did demonstrate this. You can go to these videos in here, okay? These videos in here. My channel, by the way, you can scan this code in here, and this will, if you scan this, it will take you to my YouTube channel, just to let you know. Okay, so so I did demonstrate this in these other videos, the design of these septums, okay, using either a square waveguide or circular waveguide. And did demonstrate also the one where I don't take the wave ports right at the face. I actually have a coaxial transition in there. Okay, so again, let's just see another picture of another one. This board in here is from one manufacturer. Let's take another look at another board. Another variant of this is this. And you can see that the signals, one half in here going in, amplified twice and going to the filter and amplified again. And here's another one. And here's the septum. And here's the cover, which implements the 90-degree short back end of the circle waveguide. This piece in here, by the way, is really one of these. It's this one in here. So as you can see, some of you in North America, you probably recognize this from direct TV. This is really one of those direct broadcast TV feed, LNB feed systems. So this board in here, you get basically two horns, and therefore you can get 4 signals out of this, okay? So you get one signal in here, one signal in here, and you get one signal in here, and one signal in here, and then you go through a whole bunch of other stuff. Here's another example, okay? Again, showing you the septum is right here. This is the last piece that splits the two modes, okay? And same thing, like we said, the other one. So you got basically amplification, 3 stages, image rejection filter, image rejection filter, then you combine, and then go into down conversion. Another example, okay, I don't know why I included this, but so you've got one side here, one side in here, another side in here, another side in here. Oh, this one here is not being used. Look at this. So there is a probe, but it's terminated in 50 ohm. It's not used at all. So this, I don't know why they did this. Okay, so this is to show you the bigger picture. So this is one LNB in here board. That's how it looks when you take the lid off. Basically, you have this cover, okay? But this cover in here, as you can see, this circle in here, which is beneath it, when you this is the other side, you will see this. I know why I included this is because sometimes, unlike these, where there's a cap and the divider, the last stage of the septum goes into this cabin here to divide more. Sometimes they don't. You have a BC board like this one in here, where this one is grounded in here to come on the ground from the other side of the septum to come to here. So they have they have split it. The metal cap is split in here. So that's when you put this in here. It's a little different than this one in here. Just a different variation of mechanically how you design this, okay? It's again, same thing in here. All right, here's a closer look, the same thing, okay? So this comes in, and this will be the back short for one probe, and this will be the back short for the other probe. And you can see that, by the way, I did use this device in here. That's NEC device, NEC KU band MOSFET transistors. These are with a minimum noise figure of 0.3 dB. It's extremely a super low noise device. Okay, here's another board which utilize the same thing. By the way, these boards, you can hollow the waveguide extended suction with the boards, maintaining the boards like you did in here, for instance. This one in here, they didn't put, where this one, they put a cross mechanically to stabilize it. But in this case in here, for instance, they didn't hollow anything. They just use it as is. And this is a square wave interface. It's not circular. Okay. Here's another one. Okay, uses square wave, same thing. It's square wave, but when you half it, it becomes two rectangular waves. That's how it works. That's basically implementing a septum like this one in here. Okay. So these boards, this is circular waveguide interfaced, where these ones here are a squared wave guide. Here's another one where it's circular waveguide. Okay. All right, so we did cover the, as you can see, we have a variety of these and different flavors. And so now let's go ahead and go on to the ANSYS HFSS and construct the first one. And the first one is this one in here. So basically what I'm doing is, well, let's go. What I'm going to do is I'm going to cover this and also the square wave, the square waveguide one, okay? And then what I'm going to do is go actually into both of them with different varieties of this. So let's go ahead. Now here we go. So we've got the first one. Let's start out with the square one. It's easier to understand. Okay, so we've got the square one. Okay, as you can see in here, this is a, here is the, so we start from here. The signal is fed in the common part, which is here. We call this as a common, okay? So I have a wave port comes in here, and it goes in, and there is a septum, and the septum is, let's show you the septum pieces. Okay. So we've got the septum pieces, as you can see. Okay, so we've got the septum piece that divides basically the square waveguide into two rectangular waveguides, as you can see in here. Okay, and I've got let's do this. I've got the so basically, and then what I've got a probe signal, a probe in here that is sticks right in the middle of the rectangular waveguide on each one, and then I've got a small piece of let me highlight these for you so we can. Okay, so on each side, basically, we start out with the probes. Let me. Okay, so this is the feed. This is horizontal. Okay, here's one. Let's focus on one. So I've got a probe. This is a probe that is printed on the substrate. Okay, and before the probe, there is a match section. Okay, here's a feed. The feed in here. We're talking about the horizontal one. So horizontal one. Okay, there we go. Okay, so I start out with the probe in here. Okay, and then I've got a quarter wavelength match narrower line, which is higher impedance. And then I've got a 50 ohm feed section that goes into this port in here. And then I've got a wave port in there, okay? And of course, the substrate right now, these are 4003 Rogers material, okay? So this is, and what happens is I cleared the BCB from the copper face of the waveguide. And then, of course, what I did is and this here is the extended quarter wavelength section, okay? And let me, in fact, let's go ahead, go to this one, and let me make it like this so we can show you. This is the cab. This is a cab. If you zoom in, basically, you can see that the cab has a mouse hole to let the signals come out. Now, the height of this cab is a quarter wavelength. And what it does is one wave comes in here, and it will be presented by a short wave, a short waveguide, shorted back end, and that shorted back end, because it's a quarter wavelength away from the probe, it will look like open, okay? And of course, I have a divider in there, which is part of the septum, okay? So I did this, the design of this basically is covered in the previous videos, how to design. You saw the design, you know what the waveguide dimensions, you know that. So the probe, I did cover that in the previous sessions, okay? So let's see what kind of response I got in this. So this is the input return loss, okay, which is pretty good, okay? And then let's see, this is the return loss on the microstrip, the vertical and horizontal. This one here is for the two different modes, that's at the input of the waveguide, okay? And then, of course, the transmission, you can see it right here. You can see this is the cutoff frequency for the waveguide. And you can see that it's about only 0.4 dB, 5.5 dB above the 3 dB splitting point. Now, one thing we want to make sure of is that we have, of course, when I excited this, I excited with 5 different modes for the square waveguide, as you can see that in here. So I'm putting 5 modes, and what I want to make sure of is that I want to make sure that when you look at the higher order mode, this one here is for the microstrip, okay? So right now the 2 modes, the next higher order mode, M2, is at 11.8 gigahertz. And that's what you see in here, basically, this pump in here. And you can see it also in here in the return loss. And you can see it in here. This is the suck out. As you can see, a lot of you in microwave, you can see the suck out. So usually due to higher order modes. So I can only utilize this portion of the band. Otherwise, I would have to do something to push the next higher order mode upper than this, okay? Now, let's show you how it works. Basically, what works is that we come in, the signal comes in here in square waveguide. It propagates and gradually it becomes 2 parallel waveguides, okay? Where in one of them, the signal is supposed to cancel completely, but unfortunately, we're not. This is yet to be optimized furthermore. But you can see where the hottest is here, is in this side. Okay, so let's go ahead and animate this just to show you real time how this is done. Okay, it should be getting close to finishing. Okay, here we go. So right now, the excitation, as you can see in here, let's go ahead and see this, the E field patterns, E sources, edge sources. So I've got the signal is basically one on this port, one on this port, but this port is 90 degree, okay? And when you do that, the signal basically comes in, and let me just highlight the where the septum is. Okay, so you can see, now it's a little difficult to see, but I'll make it clear right now with the, so you can see the wave is coming in here, and most of it is going on this side in here, okay? All right, so it's going to this end here, and nothing going to this one here, or much less, because it's cancels. Remember what I showed you, how the theory works out in this one in here? So what's happened is that depending on the signal was rotating clockwise or counterclockwise, you end up with the signal all basically the two modes, depending on the parallel and the perpendicular. You end up with one splitting the signal into two halves with 180 degree or phase shift, and another one that is in phase. And of course, these here, when they're on top of each other, this one with this one doubles, this one is opposite to this one, so they cancel. So the signal ends up being twice as much in here and zero on the other one, okay? And that's what you're seeing right now. So let's just prove this to you. Okay, so let me show you that if you reverse the direction of the E field, how you're going to get the signal in the other side. So we just go to the sources, fields, it is sources. What I'm going to do is I'm going to put this at 0 degree and put the other one 90 degree. And now it's going to be rotating the other way around, and it's going to be coming, and okay, there you go. You see how it comes to here, flip to the other side. Let's take a little bit, but it'll be there. Okay, here we go. You see that? You see that? I can see it also if I review this on top. Oh, no, on the bottom, sorry. You can see it, as you can see in here. You can see most of the signal going into here. Okay? And you can see it like this. You can see the, of course, yeah, the blue is the minimum signal. And you can see the signal bounces off the quarter wavelength in this section in here. So again, let me undo the change that I did, and you can see that. Come on. All right, so you can see it. Okay. Well, let's stop this, and we're going to see it on the circular waveguide one. So let's go ahead and go to this one in here. So this is exactly the same implementation, except it's a circular waveguide. Okay, so I still got in here the probe. I got one probe in here. I've got a small section in here that I added right beneath the cap in here. Okay, and then the quarter wavelength section. Okay, and then the feed 50 ohm feed line in there. Now, of course, again, what this is really doing, this portion and this is really an implementation of just this piece in here with the circular waveguide. Okay, that's what that is. And when I run this, of course, let's see what we're getting. So the first thing is this is the return loss. This is the return loss of on the circular side of the waveguide for the both modes, the vertical and horizontal. Okay, and then let's see. This is the return loss. Okay, on the microstrip ports, and this is the basically the insertion loss. Okay, and the modes. You can see that the M2 in this case is 12 gigahertz, so almost the same place. And remember that the square waveguide and the square waveguide and the circle waveguide, they're almost the same, except with just a tiny fraction, which is 0.8 of the other one. Okay, so let's get back to this. And now let's look at the E field again on this, and this should be easier to visualize because of the you can see the rotation. Okay, so you can see now in the way I got this right now set up is that the signal, as you can see, the signal comes in and the circular polarized signal comes into this side, and then gradually gets separated into the septum, and it ends up in this case going into this port. and this port becomes isolated. Okay. So let's animate this. Okay, here we go. So let's as you can see, the wave comes in on this guy. By the way, can you see which way is rotating? It's actually counterclockwise. Okay, you can see this, it's going this way. So it comes in and then it goes, and most of it goes out of this port here, and none goes out of the port in this port in here. Okay, where now again, as you can see clearly that's counterclockwise, and you can see it on here. Okay, so you can see now that this port is where the hot port is at. The signal is all leaking in here. Okay. Now let's go ahead and change the rotation of the waveguide. Let's make it a circular polarized signal. Let's make it go clockwise. Okay, so we're gonna go in here and we're gonna sources. So we're gonna go this one. I'm gonna give it 90 degree, where this one is 0 degrees. And watch what happened. Aha, there you go. It already flipped. Okay, you can see that it went on this side. Okay, and then if you look on this signal here, it's actually going clockwise now. It's rotating. When it rotates clockwise, it goes out of here and nothing goes into here. You can see the signal is destructed in here. It's supposed to be isolated. Okay, but you can only do so much finite with this. All right, so let's do something in here. What happened next is, let me just, that's this one, sorry. Like, okay, so let's look at the next one, which is basically the same thing, except what I'm going to do in here. This one, I'm going to stick a little cap on the probe. And that, according to the a lot of the publications, that ends up broadening the frequency response. And so I know that I need to work on this furthermore because I didn't get a whole lot of improvement, but you can see that it's better. It's better. Uh, but yeah. All of this, by the way, this is the return loss on the vertical and horizontal ports. And this is the insertion loss. You can see that's only 0.5 dB of insertion loss. And of course, we're still getting the M2 at 12 gigahertz in here. That shouldn't change. Okay, so let's look at, now let's look, well, we don't need to look at the E field of this because it's really the same. So on the next one, let's see what I did is, if you look at the variants that I just showed you, or we can see it on here. On some of them, they hollow the waveguide. Let's look at these ones here. So like in this one here, they hollow it, and like I said, leave only the probes. And some of them, they may not hollow it, like in this one here. And so let me see, I didn't get okay. So what I did is I hollowed the waveguide and kept the probe on a little rectangular piece that is just holding the probe on it. You see that? It's just an extension. Okay. And then what I did is I went and actually extended the last section of the septum is in one piece connected together. You can see it right there. Now, remember in the other one, let's go back. On the other one, you can see that I did not do that. Basically, let me show you this. Let me just hide this guy here. This is how this is constructed. Is there's a little PC board. The board is completely not hollowed. But what I did on one side of the board, on the other side, to common and let me hide this. Okay, this is how it's laid out. Okay, so what I did is this is your probe is here, and in the middle, because I wanted to extend the continuity, DC continuity between the septum and the piece that comes in here, and isolate the two channels. I put a little copper with a whole bunch of vias, and of course there are vias. I forgot to tell you about the vias in here. The via spacing in here has to be like designed like a substrate integrated waveguide, where you want to make sure that signal doesn't leak. Okay, and I think the right now I got them about 0.5 millimeter distances from each other. Now on the last one, okay, in here, what I did is I emptied the board. I hollowed the board so that let me hide some of this stuff. Okay, so you can see in here is that the board is hollow, and the septum is actually through the whole thing. With this one, with the substrate is only being in here. You can see the substrate that has the probe on it. Okay, this is in this case it's really it's easier to assemble, but it's mechanically this becomes very fragile. And so you can see this on the ones that I showed you in here, like in this case, for instance, you see how the this one in here where they stabilize this mechanically by making just 4 pi pieces in here, where in this case they didn't. For instance, you can see that this is what I'm showing you right now, simulated in here, modeled in here, is exactly like this one here. Okay, so it's only has the or like this one here. So you've got the probes and you got the thing sticking in there. And you hardly see any advantage of doing this, really. The reason I did this is I said maybe it might have better return loss, because the other ones when the aperture of the circle waveguide is completely obstructed by the substrate, I thought maybe it's more loss, but it really didn't have a whole lot of losses at KU band. So this is what I got, and very much the same response. So okay, so let's look at the E field again on this one here. Again, it's the same thing. Okay. All right. Okay, ladies and gentlemen. So this is it for this week. This is Dr. Mohamed Nezami again, coming to you from Garage, Jordan. Please don't hesitate to email me if you have any need for RF designs that you need to contract out. All of these designs that you see in here are on sale. If somebody's interested to purchase these, you get basically, I give you a report, I give you dimensions, all these designs are parameterized in HFSS, so you can go ahead and optimize them further or scale them. Okay. So for this, you can contact me if you'd like to purchase copies of these for industrial students. I don't do that. I don't advise students to ask for that, because they're supposed to build this themselves and learn how to do it. Okay, ladies and gentlemen, don't forget about my training if you like to come. Now, this training is customized also so that I could, if some of you have certain areas that they want to focus on, I could shift depending on the majority of the trainees. And this is on the road. I could take this training on the road for any company that has more than 5 people signing in for this. So people from Turkey, Egypt, the Gulf countries, you can actually, this is very easy and convenient for you to come to Jordan and attend this training. Where you can get to stay in nice places like this and get to visit the ancient city and other parts of this world. Okay. I again thank you very much for attending this session. I would appreciate it. Please don't forget to visit my channel and subscribe, please. I would appreciate it. The slides are going to be on my LinkedIn account. And then I'm going to also have them very soon on SlideShare. Okay? Well, until the next time, ladies and gentlemen, I do thank you for attending this session. And if you have any questions, please don't hesitate to reach out to me. Thank you very much. Thank you.